Alright, so welcome back to particle physics and the standard model. So in the last class we saw the power of using simple arguments about discrete symmetries to say something profound about nature, right. In particular we thought about the concept of parity, space-time parity or in fact spatial parity, and that thinking about it in the context of the weak interactions gave Lee and Yang the idea that the weak interactions do not respect parity, that the world as far as weak interactions go in a mirror looks completely different. There are no weak interactions in a point mirror, right, which was what Madame Wu also proved using her seminal experiment, right. So we will see how the discrete symmetries can teach us more about nature in the lectures coming up, and in particular we started dipping our toes into the concept of charge conjugation, right. So let us explore that today. Alright, so this is lecture 6, particle physics and the standard model, and we are starting to think about the concept of charge conjugation, right. What do we mean by this operator? Colloquially speaking, charge conjugation is the operation of basically changing the sign of all the charges of the state that you are thinking of, okay. And again I am going to emphasize that when we say charge, it is not just electric charge. You have to stop thinking of charge as electric charge, okay. Starting from now, stop thinking of charge as just electric charge. Think of all the global and local charges that you can assign to the particle, such as flavor number, muon number, up number and so on, right. Fermion number, baryon number, lepton number. Think of all of these and you flip the sign of that. That is the operation of charge conjugation up to a degree, okay. Today we will see what exactly we mean by that. We denote this by C, and what does this do? Remember that we have to think of particles as quantum states, right, in Fock space. That means I have to define charge conjugation as an operator that acts on a particle state. What should this do? It should return to me a state that I would loosely call the antiparticle, okay. It gives you the antiparticle. What exactly do we mean by antiparticle? We will see in the course of this course, but you get the idea, right. Antiparticle colloquially means you flip the sign of the charge, right, of all the charges. So there you go. I am going to denote antiparticle states with a bar on top. That is charge conjugation, and I think last time we also saw using the Lorentz force involving both the electric and magnetic fields, that electromagnetism is invariant under charge conjugation, right. How do we know that? Very simple. You look at how each of the elements in that equation transforms under charge conjugation. Obviously electric charge goes to a flipped sign, right, but also charge conjugation on the electric field also flips sign. Again you can see this in the simple case of an electrostatic field sourced by a point charge, right. All the field lines flip their direction when you apply charge conjugation, when you flip the sign of the charge, right. And of course the magnetic field also flips sign. Take a current, flip the charge, the current sign the current direction changes, the magnetic field direction also changes, right. And this one is a bit obvious, but I am going to write it down anyway for completeness. Charge conjugation does not flip the sign of the velocity vector. Good, okay, that should be obvious. Good. Alright, so we change all the internal quantum numbers, right, for charge conjugation. In particular it also bears saying out loud that charge conjugation does not affect dynamical quantities like mass, the energy, momentum, even the spin of a quantum state and so on. We just change the charges. Okay, good. You just flip the charges. Okay, so with this in mind, I'd like to ask you a question. We saw what charge conjugation does. So that means just like intrinsic parity, you can have an intrinsic charge conjugation or an intrinsic C number for quantum states, right, for particle states. So the first obvious question to ask is, what is the intrinsic C of an electron, right, the first elementary particle discovered in a lab in a real way, right? Think about this, pause your video for a second and think about this. What should be the intrinsic charge conjugation or intrinsic C for an electron? Okay. All right, the answer is this is a trick question. Okay, not so fast, not so fast. You can't just assign C to any state. You got to check first if the particle that you are thinking about is a C eigenstate, right? Only if it's an eigenstate you can assign an intrinsic quantum number at all, right, to that state. Good. So check for that for every state that you are thinking of. Good. Okay. So what do we mean by this? First of all, just like in the case of parity, right, we have charge conjugation applied twice on a state giving back the state. That should be obvious, right? I go to the antiparticle, the antiparticle's antiparticle is back to the particle state that you began with, right? So I apply it twice, I get back the original state. Good. Now the implication of that is that the eigenvalues of the C operator are plus or minus 1. Okay, obvious? Good. They have to be real. I can't, right, exactly. So they have to be real. So they only take two values, plus or minus 1. Okay. Now that further implies that since the charge conjugation operator takes me to the antiparticle, if it's an eigenstate, I have plus or minus the original state for an eigenstate, right? If eigenstate. Okay. Now what does this mean? Let's stare at these two parts of the equation. Physically, this automatically means that this only makes sense, let me switch color, only makes sense if, in fact I wanted to connect these parts also, right? If phi bar and psi bar and psi are the same particle species. Agreed? I want psi bar to be plus or minus psi as a quantum state, right? Right, as a physical state. Good. In other words, the particle should be the antiparticle. There are very special states where this is true. Those are the only states for which those are the states that qualify as good candidates for being charge conjugation eigenstates. Very good. So what does that mean? It means the electron is not a C eigenstate, because obviously the electron is not the positron, it is not its own antiparticle. Okay, very good. Then what are the C eigenstates that we know of, right? from the menu of particles. So, who is invited to the C party, in other words, correct? So, let us write down some C eigenstates that we know of, and again I encourage you to pause the video here and think about this for yourself. Think of some particles that you know of that are their own antiparticles. Okay, so I am just going to start listing. Obviously, the photon, right? We do not talk about antiphotons. The photon and the antiphoton are the same, one and the same thing, right? What else? We talked about pions, and in particular we talked about neutral pions, right? Remember pion, I wrote this as this state I wrote as a linear combination of UU bar and DD bar, correct? So, now you exchange U and U bar and D bar, you get back the same state. So, you know, pion is its own state, and there are further mesons. There is something called a meson tower. You might encounter this in your assignment. There are eta mesons, eta prime meson, rho meson, and so on. Notice that these are all electrically neutral. That is at least, you know, one criterion that you need to have. Not all electrically neutral particles are their C eigenstates, but it is necessary but not a sufficient condition. Okay, good. Now, here is a question for you to think about. What about the neutrino? Is the neutrino a C eigenstate? Okay. Now, some of you may have heard that, you know, if the neutrino is Majorana, you may have heard this in talks on YouTube videos and so on, right? If it is Majorana, it implies that neutrino is its own antiparticle, and then if it is Dirac, you know, it is not. You may have heard this, right? Now, I am going to encourage you to stop thinking in terms of these words. Okay, this is not how you do particle physics. Antiparticle, the word antiparticle has very subtle connotations which we will encounter in this course. Okay, you cannot really fit all of physics into the English language. The things are more subtle. So, if you think in terms of this, it is natural to think that neutrino is its own eigenstate. It's a charge conjugation eigenstate, right? No, not really. Okay, let us see how. The reason is, remember when we talked about intrinsic parity and the weak interactions and so on, we said that neutrinos have been observed only as left-handed states. Left-handed meaning in terms of helicity. Neutrinos, when they propagate, their spin is such that, you know, the corkscrew is turning to the left, right? So, they are only seen with left-handed helicity. The correct thing is they actually have left-handed chirality, but as far as laboratory experiments, laboratory measurements go, they have left-handed helicity, right? So, when I say neutrino, immediately start thinking it is a left-handed particle. Electrons are both left and right circular polarized. Photons are both left and right circular polarized. Neutrinos are only left polarized. Never forget that. Okay. In that case, I have to actually write the neutrino state with, you know, an L subscript. I should always remember that, right? Now, if I apply the charge conjugation operator on that, whatever be the eigenvalue plus or minus 1, I should at least flip the I should at least turn it into an antiparticle, an antineutrino, and then I should ask whether that antineutrino is the same as neutrino, right? But when I do that on this operation, I am getting an antineutrino that is left-handed. Now, that is not allowed, right? Neutrinos are left-handed, antineutrinos are necessarily right-handed. So, actually let me not write it this way, let me just erase this. So, antineutrinos are right-handed, right? But I have just written a left-handed antineutrino. That is not possible. That tells you that even at this stop, right, before you go to writing the actual eigenstate, even here you are not allowed to do this operation. So, neutrinos are not their own eigenstates, okay? Their own C eigenstates, I am sorry. Very good. Now, let us keep going, okay? We just wrote down some C eigenstates, but what are the eigenvalues, right? So, it is very instructive to know the C eigenvalues. Since C is an intrinsic quantum number, it is part of the fingerprint of every species. Okay, when you go to the particle data group book and look at particle species, you would see not only its mass and charge and spin listed, you would also see the angular momentum, parity, charge conjugation. They are all part of the particle's fingerprint, and they all matter a lot because that tells you what processes are allowed, what is forbidden. Okay, so I am just trying to motivate why I am doing this. All right, good. So the C eigen value of the photon, what is it? Again, think for a second. Okay, always pause your videos and think for a second. But I am going to write down the answer now. Is it plus or minus 1? It turns out it is minus 1. Why did I write that? What is the physical meaning of this? This is because I know that the photon arises as an excitation of a field. It is not the E field, it is not the B field that you see in Maxwell's equations, it is actually the vector potential. Okay, sorry, let me write it in 4, we are in quantum field theory. So it is actually the vector potential, in particular the 4 vector potential, the 4 potential, right, that you encounter in electromagnetism. Just to jog your memory, where does this come? The electric field, you can write in terms of a gauge potential and vector potential, right. This forms the total A field, and of course the magnetic field can be written as a curl of the vector potential, and there is a neat way to write this, right. Together we just write this in terms of this, at least in the Lorentz gauge, right. This you must be familiar with from electromagnetism. So now I know that in charge conjugation what happens, E flip sign, right, that means, and then the grad does not flip sign under charge conjugation. So both the A0 and the A vector flip sign. Similarly B flip sign, so since the curl does not flip sign, since the grad does not flip sign, again the A flip sign. So that tells me that since the field from which you get the particle excitation in Fock space flips sign under charge conjugation, if I act C on gamma, I should get a minus sign as the eigen value. Okay, let us take it one notch further now. What is the eigenvalue of a fermion anti-fermion pair? We saw what it was for parity, but what happens if I act charge conjugation on it? Okay, this is hard to guess. Okay, so I am just going to write down the answer. The eigenvalue, now I am writing the eigenvalue, right, I am not writing in terms of eigenstates. Note that the eigenvalue turns out to be minus 1 power the orbital angular momentum L plus the spin angular momentum S. Okay, so how do I know that? All right, this is a little more little subtle, but do follow along. Okay, this is what particle physics is all about. So there are 3 steps. So let me just write that there are 3 steps we have to consider to get this value. The first is if the angular momentum, the orbital angular momentum of the pair is L, the total angular momentum, right, fermion pairs have total angular momentum. If that is L, then acting charge conjugation would give minus 1 power L from the apparent switch in position. Again, this is from the parity eigenvalue. Okay, let me explain what I mean by this. So I have a fermion, right, and an antifermion. If I apply charge conjugation, what happens? I get, if I apply charge conjugation, this flips to a antifermion and this flips to the fermion, right? It looks like I have applied parity now though, correct? Apparently it looks like apparently the F and F bar have switched in position. So I might as well apply the parity argument from lecture 4 or lecture 3, I forget, okay? Go look it up. Lecture 4 or 5, I am sorry, 4 or 5 we did for a fermion antifermion pair or for any fermion pair, for the total angular momentum, if I apply the parity operator, it becomes -1 power L. That is just what I have done, okay? That is the first step. Next, I also have a factor of -1 power S plus 1, where S is the total spin of this fermion antifermion pair, okay? Again, how is this possible? You probably are familiar with singlet and triplet states, right? In quantum mechanics you would have learned that I can put two fermions either in a spin singlet state or in a spin triplet state, correct? Let me jog your memory on that. The spin singlet state, okay, let me write that as S equal to 0. That is what we mean by spin singlet, right? Why? Because for the total S equal to 0, I can only form this superposition, right? Oh, I am sorry, I wrote exactly the sign, exactly flipped the sign, just the opposite of what I wanted to say. Good. It can exist, the spin singlet exists only in the superposition where you have one spin up and another spin down minus the other spin down and the second fermion with spin up, correct? And this, what is this? Is it symmetric or antisymmetric under the exchange of the two fermions? It is obviously antisymmetric, right? So I am going to write exchange antisymmetric, because if I flip the up and down, the wave function here, the state here basically flips sign, correct? Whereas the triplet state that I can form with the two spins, right, I can form three kinds of triplet states. I can have an up and up, half plus half giving me total of 1, and obviously I can then also have down and down, right? Again the magnitude of the total spin is 1. What else can I have? I can also have this, right? The okay, the total spin is always 1 for all of these configurations, right? That is how quantum mechanics works. Right, and this notice has a plus sign as opposed to the one in the singlet state. So all of this are obviously exchange symmetric. What are we exchanging here? The two spins in each of the states, correct? So what does that tell me? If I were to apply charge conjugation, that is also an exchange, right? Again the same concept as here, F and F bar are being exchanged. That means if I apply charge conjugation for the S is equal to 0 state, I pick up a minus sign. That is what this captures, that is what this one captures. I have to put -1 power 0 plus 1, so that is the -1. If I exchange the fermion and antifermion, but it still remains a symmetric state, then I do not pick up a minus sign, I just have a +1, and that is what again this captures. If I put a 1 here, I get -1 square, correct? Okay, excellent. What is the third step? So the third step is that just from interchanging a fermion and an antifermion, I would pick up a -1, okay? Now this explaining this is beyond the scope of this course at least, and for the curious among you, what I recommend is go to Srednicki. He has and in particular his chapters on spinors, okay, and for the more brave hearted among you, go check Gottfried and Weisskopf's book on quantum field theory, okay. These are all quantum field theory books. This is where they explain in terms of quantum field theory, in terms of spinor exchange, in terms of how spinors move around within Feynman amplitudes, the fact that when you interchange f and f bar in any quantum state, regardless of actually whether you switch them or not, it's sometimes called fermion ordering. When you do this, you pick up a minus sign for fermion antifermion exchange, okay. So that I am not going to get into right now. But what has happened now? Charge conjugation, by now it must have been clear, is a multiplicative quantum number, right, and that means I have to now put them all together. So the total charge conjugation of a fermion antifermion pair is minus 1 power L times minus 1 power S plus 1 times minus 1, all the three factors we just talked about. So I can just write this as minus 1 square I can take away, and I just have L plus S. That's it. Good? Good. Okay. What are the implications in the real world of this exercise? Where do we find fermion antifermion pairs? Well, they're handed to you as a bound state in mesons, correct? So mesons are fermion antifermion pairs, bound states of them, right, already. So in particular, that means for pseudo scalar mesons, L is 0, S is 0, right. S has to be 0 for scalar mesons, right, and because I say pseudo scalar because when L is 0 under parity minus 1 power L minus 1 power L plus 1 you get basically, right. Okay, so that because it's a fermion you get an extra minus 1, right, so it gives you a minus 1, so that makes it a pseudo scalar. So an example would be pions. That's the face of the pseudo scalar meson. For this configuration you have C equals minus 1. Oh, I am sorry, C equals plus 1, correct, putting it into this formula. L plus S is 0, so I get C equals plus 1. Okay, what about vector mesons? Again, the first vector meson one can think of is the row meson. For this I have L equals 0 and S equal to 1, alright. Why? Again, under parity P is minus 1 power L plus 1 for a meson, and if it is a vector I need minus 1, that is why I need L equal to 0, but again if it is a vector the spin is 1, the total spin is 1, that is what makes it a vector, right. For that the charge conjugation eigen value is minus 1, okay. Now what is the implication of that? It means it is totally fine for me to have a pion going to 2 photons. Why? Because a pion has a C of minus 1. If I have 2 photons, this being a multiplicative quantum number, I have minus 1 times minus 1 on the right hand side, right. So that is good. Can I have a pion going to 3 gammas? Obviously not, right, because on this side it is minus 1 and on this side it is plus 1, the C quantum number, right. And I can write similar, I can always check whether a process is allowed or not. For example, I can take an omega meson, and if I want to see what it decays into, would it decay into a pi 0 and a gamma, it turns out yes, because On the right hand side C is minus 1, left hand side also turns out C is minus 1, okay, because it is a vector meson, we just saw it is minus 1, right. But can an omega go to a pion plus 2 gamma? No, right. Why? Again C is minus 1 here, but it is plus 1 here on this side, okay. So this is the trick that you can use again and again to check whether a process is allowed or not, okay. There are other neat consequences. For instance, Griffiths talks about, I think it is in one of his problem sets if I am not wrong, Griffiths talks about the confirmation that strong interactions preserve C came from this very neat experiment where the experimentalists crashed protons and antiprotons, and they were looking at the final state of pi plus, pi minus and pi 0, okay. Now using this they set very stringent limits on the violation of C, or in other words they conducted a very good test of the validity of the C symmetry in strong interactions. How did they do that? They looked at the spectra of the energies of the two charge states, okay, and they found that these two spectra, right, what do you mean by spectra? So you have the number of particles that you get of a certain energy and then you bin it as a histogram, right. So you basically get something like this, you get a spectrum, and they found that this spectrum for both pi plus and pi minus are identical, okay. Now that told them that C has to be a good symmetry, because I can flip the pi minus and the pi plus and nothing seems to have changed in the measurement, right. So that is the 0th order understanding of this. If you want to think about it more, you can go read Griffiths. So okay, so with that I will end this section, I will end this lecture. In the next lecture we will see further implications of C. We will put C and P together, that is where the fun is, and then we will also put C and P and T, time reversal, together. Think about what is known as the CPT theorem. It is a very fundamental deep theorem. We will probably look at the proof of that, and then finally we will get on to time reversal, okay. So I will end here, see you later, thanks.